As the continuation of the previous discussion, let us embark on two new parameters known as admittance and impedance. To understand admittance and impedance, let us consider the case of a RL circuit. The instantaneous voltage that is applied across the series combination of L and R is given by V complex T. This is equal to E0 e raised to I omega t. This can again be written as V complex e raised to I omega t, where V complex will be having only the real part, so that V complex can be written as E0. The complex voltage results in a complex current IT in the circuit, which is I e raised to I omega t. We define the admittance as a parameter Y, which is equal to the complex current over complex voltage, where we have the complex current as given by I0 e raised to I5, where I0 is equal to E0 over square root of R square plus omega square L square, and tan phi equal to minus omega L divided by R. But as defined, the complex voltage V will be having only the real part, and that is equal to E0. Therefore, the admittance is given by I complex divided by V complex, and this is equal to E0 over square root of R square plus omega square L square e raised to I phi multiplied by 1 by E0. E0s gets cancelled. Therefore, Y is equal to e raised to I phi divided by square root of R square plus omega square L square. So this is admittance in the case of a RL circuit. We'll denote impedance Z as a reciprocal of Y, and its units is ohms. We shall now try to find out the expressions for admittance and impedance in the case of a RC circuit. So as before, we have E complex equal to E0 and I complex as equal to I0 e raised to I phi, where I0 equal to E0 over square root of R square plus 1 by omega c the whole square, and then tan phi as given by 1 by R omega c. Therefore, the admittance is given by I complex over V complex, and that is equal to E0 over square root of R square plus 1 by omega c the whole square e raised to I phi multiplied by 1 over E0, which is equal to e raised to I phi divided by square root of R square plus 1 by omega c the whole square. Now let us find out the admittance and impedance in the case of a circuit which is containing only a resistor. In this case, we will find that the impedance is a real quantity, and that will be simply equal to R. Let us borrow the expression for the phase angle from a RL circuit and then write tan phi as equal to minus omega L divided by R. Since L is equal to 0 in the circuit, we conclude that the phase angle is equal to 0. Therefore, e raised to I phi will be equal to e raised to I times 0, which is equal to e raised to 0 and that is equal to 1. We'll take the expression for admittance from a RL circuit and then write y as equal to e raised to I phi divided by square root of r square plus omega square L square. In this case, L is 0 and then e raised to I phi is 1. Therefore, this expression simply reduces to 1 over R. So admittance is 1 over R and we see that the impedance, which is 1 over Y, is equal to R. The voltage current relationship now becomes Ohm's law V equal to Ri. Let us represent the voltage and current in the complex plane in the case of a circuit which contains only a resistor. The x-axis is the real part and the y-axis is the imaginary part. The complex voltage is simply equal to E0 and the complex current, which is given by I0 e raised to I phi, this is equal to I0 multiplied by 1, that is equal to I0. So in the case of a circuit containing only the resistor, the voltage and current are real quantities. And the phase difference between the voltage and current, phi, is equal to 0. Also, the relationship between V and I is linear. Therefore, we can plot the voltage as like this. So this is voltage and the current, which will be having a phase difference of phi equal to 0, can be represented like this. That is, in a complex plane, the voltage and current are in phase for a circuit containing R alone. We shall now consider a circuit containing only an inductor. In this case, the phase angle tan phi is equal to negative of omega L over R. In the ideal case, R will be equal to 0, but in practice we cannot completely neglect the value of R. Therefore, we can take R as approximately equal to 0, or R will be having a very low value. So from this expression we will get phi as equal to negative of pi by 2. Therefore, e raised to I phi, this is equal to cos of minus pi by 2 plus I sin pi by 2 minus pi by 2, and this will be equal to minus I. Therefore, the admittance Y is equal to e raised to I phi divided by square root of R square plus omega square L square, and R is approximately equal to 0. Therefore, this is equal to negative of I divided by omega L. The voltage in the circuit is E0 and current in the circuit is I0 e raised to I phi, that is equal to minus I times I0. The factor minus I means that the current oscillation lags the voltage oscillation by pi by 2 in phase. As before, let us try to plot the complex voltage and complex current in the complex plane. This is the real axis and this is the imaginary axis. Let us first fix the complex voltage. So this is the complex voltage. We saw that V complex is equal to E0 and then I complex as equal to minus I times I0. and phi equal to minus pi by 2. Therefore, the current would be like this, and the phase angle between these two would be phi equal to pi by 2. That is, in the inductor, the current lags the voltage. We shall now consider a circuit having just a capacitor. For such a circuit, the phase angle tan phi is equal to 1 by r omega c. R is approximately equal to 0. Therefore, we'll get phi as equal to pi by 2. Now, e raised to I phi equal to cos of pi by 2 plus I sin pi by 2, which will be equal to I. The admittance y is equal to e raised to I phi divided by square root of r square plus 1 by omega c the whole square, that is equal to I over 1 over omega c, and that is equal to I times omega c. The corresponding current oscillation would be I complex equal to I0 e raised to I phi, and that is equal to I times I0. The factor plus I means that the current oscillations leads the voltage oscillation by pi by 2 in phase. So as before, we'll fix the complex voltage first, that is V complex, which is equal to E0. Now the current will lead the voltage by a phase angle of phi equal to pi by 2. So this is the complex current, which is given by I times I0. That is, in a capacitor, the current leads the voltage. We have now understood the parameters impedance and admittance. We shall now discuss the use of impedance and admittance in solving electrical circuits. The impedance and admittance will come handy when we want to solve electrical circuits having parallel or series components. In this figure, the two gray boxes show some electrical components that are connected in parallel. For example, inside this, there can be a series resistor and a capacitor, and inside the second box, we can have an inductor like this. So we have a resistor and capacitor in the first box and just an inductor in the second box, and we want to solve such kind of a circuit. And these two boxes are in parallel, and when we have such kind of a combination, we can conveniently use the admittance of the circuit to solve the currents and voltages in the circuit. Let us assume that we have somehow found out the admittances of the two boxes. For the first box, the admittance is y1, and for the second box, we have found out that the admittance are y2. And these boxes are connected in parallel. We find that the voltage across the two boxes are the same. If the current coming to the junction is I, the current that is flowing to the first box is I1, and the current that is flowing to the second box is I2. We can write the total current as being divided into I1 and I2. In terms of the admittance, we can write Y1 V complex plus Y2 V complex, because the two black boxes are at the same potential V, and therefore this is equal to Y1 plus Y2 times V. This implies that the equivalent single black box has an admittance Y equal to Y1 plus Y2. This is the equivalent value of the admittance, which is equal to Y, and Y is equal to Y1 plus Y2. in summary, if we have a circuit containing parallel circuit components, then we can find out the admittance of the circuit to solve the expression for the total current in the circuit. We shall now consider the case of elements which are connected in series. As a practical example, let us consider that this contains a resistor and a capacitor, and this contains a inductor L. When a current I flows across the circuit, there will be potential drops V1 and V2 across the two circuit elements. Therefore, we can write the total voltage as equal to V1 plus V2, and V1 can be written in terms of the impedance as Z1I plus Z2I, and therefore this is equal to Z1 plus Z2 multiplied by I. That is, the series circuit that we have been considering can be simplified having just a single element with impedance Z equal to Z1 plus Z2. This is shown in the second figure, where the series combination of Z1 and Z2 has been replaced by a single element Z, and the potential drop across Z would be V1 plus V2. That makes us equipped to study the steady states in circuits containing a sinusoidal voltage source by the third method, that is the method of complex impedances. We shall study that in the next video.